All right, we're going to dive into a concept that is, quite literally, powering the world around you, from your phone all the way up to the entire power grid. We're talking about magnetic reluctance.
So let's kick things off with a pretty simple question. We all know magnets are strong, right? But can you actually block their field? Like putting up some kind of magnetic insulator?
Well, the answer is kind of surprising. Turns out you can't really block a magnetic field like you'd block light with your hand. The field lines are always there. Instead, the whole game is about redirecting them, giving them a path that's just way more appealing to follow.
I love this way of putting it. It's not about building a dam. It's about digging a new river channel. You introduce a material that basically just soaks up those magnetic field lines, guiding them exactly where you want them to go and away from where you don't.
To really get this, we've got to stop thinking about magnetism as this, mysterious, magical force. We need to start seeing it for what it is, a circuit. It's like an invisible river with its own current and its own set of obstacles.
So first, let's talk about the flow in our river. That's what we call magnetic flux. It's basically the total amount of the magnetic field passing through an area. Think of it as the magnetic version of current.
And, just like an electrical current runs into resistance, our magnetic flux has its own form of opposition. It's called reluctance. You can picture it as rocks or sharp turns or shallows in the riverbed that make it tougher for the water to get through.
And this is where it gets really cool, because the analogy to the electric circuits we all learned about is almost perfect. It's like a Rosetta Stone. The push from a battery, voltage, has its parallel in magnetomotive force. The flow of electrons, the current, is just like our magnetic flux. And that opposition, resistance, is a perfect match for reluctance.
Okay, so if reluctance is the opposition, how do engineers actually play with it? How do they design things like motors and transformers? How do they, carve that perfect riverbed?
Well, they use this simple but incredibly powerful formula. It's like their secret recipe. See, reluctance really just comes down to three key ingredients: the length of the path the magnetism has to travel, the area of that path, and what the path is made of.
This gives engineers three main levers they can pull. First, length. The longer the path, the more opposition. Makes sense. Second, area. A wider, thicker path, like a big, wide river, makes it way easier for the flux to flow, so that lowers reluctance. And third, and this is the big one, the material itself.
That third lever is a property called permeability. We use the Greek letter mu for it, and it's basically just a measure of how magnetism-friendly a material is. A material with high permeability is like a perfectly smooth, super deep channel for our magnetic river to just glide right through.
And this is where it gets kind of mind-blowing. Look at the staggering difference between materials. Air has a permeability of about 1, but pure iron, it's about 5,000 times more permeable. And then you get to special alloys like mu metal, and you're looking at over 100,000 times more permeable. This is exactly why a transformer core is made of iron and not, well, just air.
So the goal, if you're trying to build something really efficient, is to create a low reluctance superhighway for that magnetic flux. You grab a material like soft iron, you make the path as short and direct as you can, and you make it nice and wide.
But of course, nothing's ever perfect, right? Just like any river, even the most perfectly designed channel is going to have some leaks and overflows, especially when you get into the real world.
Yeah, no magnetic circuit is ever 100% perfect. Engineers always have to deal with a few little imperfections.
Okay, so the first imperfection is something called leakage flux. This is where some of the magnetic field lines just decide, nah, I'm taking a shortcut, and they escape the main path, leaking out into the air around it instead of sticking to the route the engineer built.
The second thing is called magnetic fringing. It's kind of funny. The field lines actually push away from each other. So when they have to cross a gap, like the air gap in a motor, they don't just go in a straight line. They bulge outwards, which actually spreads the field out a bit. And this is why the actual physical shape of the circuit is so important. As one source points out, sharp corners are just awful for containing a magnetic field. It's like trying to get a race car to make a 90-degree turn without slowing down. The field lines are just going to crash through the corner and leak right out.
Okay, so we've talked about all these invisible rivers and obstacles, but why does mastering all this stuff really matter? Let's look at how this builds the tech all around us.
Because here's the really clever part. Understanding reluctance isn't just about getting rid of it. It's about being strategic. Sometimes, like in a transformer, you want an ultra-low reluctance path to guide energy as efficiently as possible. But other times, like in the air gap of a motor, you deliberately create a high reluctance path because that's where the magnetic force actually does the work to create motion.
And this control is the secret sauce behind our modern world. In transformers, it means we can move power around with over 99% efficiency. In motors, it's literally what makes them spin. For sensitive electronics, it's the shielding that protects them. And in an MRI machine, it's what allows us to see inside the human body with incredible detail.
So, the huge takeaway here is that reluctance isn't just some passive thing. It is a powerful design tool. By carefully carving out these invisible riverbeds, some wide and smooth, some rocky and narrow, we can tell one of nature's most fundamental forces exactly where to go and what to do when it gets there.
And that leaves us with a final thought to chew on. We've said reluctance is opposition and permeability is acceptance. So, what happens next? What happens as we start to engineer materials like superconductors, which have almost zero opposition to magnetism? What kind of new possibilities does that open up?